Picture this. You're sitting in your living room on a really sweltering July afternoon.
Just trying to stay cool.
Right, exactly. Inside, you're perfectly comfortable. You're just enjoying that steady, quiet kind of background hum of your air conditioner.
It's basically white noise at that point.
Yeah, exactly. You're reading a book, maybe watching a movie, and then out of nowhere, the machinery outside just completely shatters the peace.
Oh my.
Like a sudden violent bang, or maybe this high-pitched screech, or an aggressive electrical buzz that just makes you instantly pause the TV, stand up, and stare out the window in total panic.
It's completely visceral reaction, right? I mean, we're biologically wired to react to sudden loud noises anyway.
Right.
But when it's coming from the specific machinery that, keeps your home habitable in extreme weather,
It's terrifying.
it really is. It triggers this very specific kind of dread. You're suddenly just acutely aware of how dependent you are on that metal box sitting out your backyard.
And usually, when we talk about a complex machine breaking down today, we expect like digital precision. You plug a diagnostic tool into a modern car, it spits out an error code, and you know exactly which sensor failed.
Yeah, cars are easy that way now.
But with a residential HVAC system, we're largely relying on our ears. We're dropped into this auditory diagnostic landscape that feels pretty murky for the average homeowner. We hear a noise, but we don't speak the language.
Which is exactly what we're going to decode today in this deep dive.
Yes.
We're drawing entirely from the field expertise of Dave Hartzell. He's a NATE certified master HVAC technician, and he has exactly 47 years in the trade.
Wow, 47 years.
Yeah. He owns Hartzell's Heat and Air down in Kingfisher, Oklahoma. And his foundational philosophy, it's really what makes this so fascinating.
What's the philosophy?
Well, a healthy air conditioning system is quiet by design. When you have balanced parts rotating in perfect harmony, the acoustic output is, minimal and steady.
So by definition, noise equals change. Like some part of that physical equilibrium has just been violently disrupted.
Yes, exactly. When a new sound shows up, a component has either come loose, worn down, gotten dirty, or it's straining under a massive physical load.
Right.
So our mission today is to translate these specific frequencies. We're going to break down the mechanics behind the noise so you actually understand what's failing inside that box.
And I really want to focus on the physical mechanics here, I want to know the why and the how.
Sure.
Because if you understand what's actually happening when the machine rattles versus when it, grinds, you can figure out whether you just need to clear some brush or if you need to sprint to the thermostat to kill the power.
Before the whole system just eats itself, right?
Exactly. I kind of compare it to a baby, An AC unit can't tell you exactly what's wrong with words, so it communicates through different kinds of crying.
That's a great analogy.
Yeah, so our job today is to figure out if it's just a little fussy or if it needs a doctor right now. Let's start with the most common and probably least destructive acoustic change, the rattle.
Okay, yeah. Rattling is usually your baseline mechanical disruption. When you hear a rattle, you're generally listening to something that's loose or foreign debris that somehow infiltrated the outdoor unit.
Which happens a lot.
Oh, constantly. Think about the sheer volume of air a residential condenser unit moves. I mean, that fan is pulling thousands of cubic feet of air per minute right through the metal fins of the coil.
It's essentially a giant outdoor vacuum cleaner.
It really is. Pulling in every dry leaf, twig, and piece of gravel the wind happens to kick up.
Right, and when a dry stick gets sucked in and the fan blade just continuously flings it against the metal grate.
You get a really harsh, erratic rattle.
Yeah.
But the physics of a rattle gets a lot more interesting when it's not external debris. The system naturally produces a low-frequency vibration when the compressor is pumping and the fan is spinning at, 800 RPM. Over time, that constant harmonic vibration actually causes metal fatigue.
So a screw on one of the outer service panels just slowly backs itself out over a few years of running.
Exactly. And once that screw is loose, you have two pieces of thin sheet metal just vibrating against each other. They hit a resonant frequency, and suddenly you have this surprisingly loud, annoying rattle just echoing against the side of your house.
Okay, so given that it's mostly external debris or a backed out screw, I'm assuming the protocol here is pretty straightforward. You just, you cut the power at the main breaker.
Yes, absolutely.
Because we are never sticking our hands into a running fan.
Never.
Right, and you just do a visual sweep, pull out the sticks, grab a screwdriver, and snug up the panels.
It's kind of like getting a pebble in your shoe, right? Annoying, but a simple physical fix.
That is the entirely safe homeowner-level diagnostic. You're just removing physical interference and restoring the structural integrity of the casing. But, okay, what if I go out there, I clear all the autumn leaves, I meticulously tighten every single screw on the chassis, I turn the power back on, and the rattle is still there?
Ah.
Like, maybe it sounds deeper inside the machine? I'm guessing I've crossed a boundary at that point?
You've hit the nail on the head. If the sound is radiating from deep inside the unit where you just can't easily see it, your DIY journey is over.
End of the line.
Yeah. It could be an internal bracket that holds a critical component or a fan blade that's become slightly deformed and is spinning out of balance.
Oh, wow.
And when a fan blade loses its perfect equilibrium, the eccentric rotation sends violent vibrations right down the motor shaft.
Yeah.
You really don't want to go dismantling the inner workings of the machine to hunt that down.
No, that makes total sense.
Yeah.
And it's one thing when physical objects hit each other, but sometimes the noise isn't structural at all. It's the sound of energy failing to move.
Yes.
Let's talk about buzzing, because reading through Dave Hartzell's notes, this seems to sit entirely in the realm of electromagnetism.
Buzzing is a completely different beast. You're no longer dealing with a physical object hitting another physical object. You're hearing actual electrical strain.
Okay.
You're hearing alternating current struggling to bridge a gap or, power a failing component.
Mm-hmm.
And the most common culprit here is a part called the contactor.
Right, and the contactor is basically a heavy-duty relay switch, isn't it? Like the thermostat inside the house sends a low-voltage signal out to the unit, and the contactor uses that low voltage to close a heavy switch that unleashes the high voltage to the compressor.
That's the exact mechanism, yeah. The contactor uses this small electromagnetic coil.
Yeah.
So when your thermostat calls for cooling, it sends 24 volts to that coil,
Okay.
which creates an electromagnetic field strong enough to pull a set of heavy metal contacts together, and that closes the 240-volt circuit.
Got it.
But here's the catch. We use alternating current, which cycles 60 times a second. So as the contactor wears out, or if, say, dirt gets between the magnetic plates, that electromagnet struggles to hold the switch closed against its tension spring.
Oh, so it's essentially snapping open and shut 60 times a second, because the magnetic field keeps failing and catching.
Exactly, which manifests as a really aggressive, rapid chatter, or this loud electrical buzz.
Wow.
The voltage is literally racing across the contacts as they bounce. It's incredibly stressful on the equipment.
Right. And the other major source of buzzing is the start capacitor. I want to spend a minute on the physics here, because the concept of electrical inertia is just fascinating.
It really is.
Because a motor sitting still requires a massive surge of energy just to break its static friction and start turning, right? It's kind of like a car battery trying to crank over a heavy engine.
Exactly. We call that locked rotor amps.
Mm-hmm.
The amount of energy required to get a heavy compressor core or a fan blade moving from a dead stop is exponentially higher than the energy required to keep it running once it's already in motion.
Right.
So the start capacitor's entire job is to store up a massive charge of electrical energy and dump it all at once to create a phase shift in the motor windings. It generates the raw torque needed to break that inertia.
But the fluid inside those capacitors, the dielectric fluid, it breaks down over time, right?
Yes.
It loses its microfarad rating. So when it fails, the motor is just sitting there receiving standard running power, but it doesn't have that extra kick to actually start spinning.
The motor just sits there locked in place, absorbing electrical current that has nowhere to go.
Oof.
And that current just turns into pure heat and a very loud, struggling electrical hum or buzz. The motor wants to turn, but the electrical force just isn't there to achieve the required torque.
So if I'm hearing a loud electrical buzz, I assume my immediate action is to not touch a single thing and just call a pro. I mean, just like you wouldn't poke around a live municipal power box, you shouldn't mess with this.
Absolutely.
Because even if I cut the breaker, a capacitor's literal job is to store a massive electrical charge. I'm assuming it doesn't just magically empty itself the second I flip the switch.
No, it definitely doesn't. The voltage inside a capacitor can be lethal even when the main power is completely severed.
That's terrifying.
Yeah, they carry real dangerous voltage long after the system is off. So if you hear that persistent electrical buzz or a chattering contactor, you have an absolute do-not-touch situation. A professional knows how to safely discharge the capacitor and test the ratings with specialized meters.
Okay, so we've covered external physical rattles and internal electrical buzzing. Now we have to talk about the sounds that basically mean, the sky is falling.
And stuff.
Right, the severe mechanical failures, the screeching, the grinding, and the banging. If rattling is a loose screw, this is the sound of active, severe physical destruction.
This is where every extra second you allow the system to run is causing cascading physical damage.
Wow.
Let's break down the mechanics. A high-pitched screeching or squealing sound almost always points to bearing failure.
Okay.
The bearings are the critical interface that allows the motor shaft to spin smoothly within the housing.
Because they're taking all the physical load and the heat generated by the motor.
They're subjected to intense thermal loads, yeah. So over years of operation, the protective lubrication inside the bearing, whether it's a sealed ball bearing or a sleeve bearing, it begins to thermally degrade. The boundary layer of oil literally cooks off.
Yikes.
And once you lose that micro-thin layer of lubrication, the friction skyrockets. The metal surfaces begin to drag against each other, producing that terrible high-pitched screech.
And if you just ignore the screech, turn up the TV to drown it out, I'm assuming that boundary layer of oil vanishes completely,
Yeah.
and you escalate straight to grinding.
Grinding is the sound of total structural breakdown. The bearing hasn't just lost its lubrication, the metal itself is failing.
Oh, man.
Without that protective barrier, the internal steel parts of the motor are actively micro-welding and tearing themselves apart. They are literally grinding themselves into metal shavings.
Just hearing the phrase metal shavings near high-speed machinery makes me cringe. But what about banging or clanking? That sounds heavier than a bearing issue. It's much heavier. Banging or clanking usually indicates that substantial internal parts have broken their physical mounts and are violently slamming around inside the casing.
Okay.
And the most critical version of this is a hard, heavy bang right when the system starts up or shuts down. That often means the internal suspension of the compressor has failed.
And the compressor being the massive heavy cylinder inside the outdoor unit that actually pumps the refrigerant.
Right. The compressor is hermetically sealed in a welded steel shell. The actual pumping mechanism inside that shell, the heavy scroll or reciprocating core, is suspended on heavy-duty springs to absorb the violent torque of starting and stopping.
Okay.
If one of those internal springs snaps from metal fatigue, the entire heavy iron core slams violently against the inside of the steel shell every time it kicks on.
That is absolutely terrifying.
Yeah.
So applying our deductive logic here, if I hear a screech, a grind, or a heavy bang, I am not waiting for the house to cool down. I am sprinting to the thermostat and killing the system instantly. You shut it down immediately. You do not let it run for another 10 minutes to see if it sorts itself out. You absolutely cannot fix an internal compressor issue or a scorched bearing from the outside.
So is this like driving a car with a flat tire? Or if you just keep driving to get home, you end up destroying the entire wheel?
Exactly. Because running a motor with a grinding bearing or forcing a banging compressor to keep violently shifting on broken springs, it turns a localized failure into a massive cascading system-wide event.
Right.
I mean, if the compressor internals are grinding, those metal shavings don't just stay in the compressor.
Oh no, they get pushed out into the lines.
They get forcefully pumped through the entire closed loop of the system. They contaminate the copper lines, they clog the tiny metering device indoors, and they lodge in the evaporator coil. The machine is actively destroying itself, and it's literally begging you to stop by projecting that destruction acoustically.
Shut it down. Message received. Now, we've talked about these very loud, violent mechanical noises, but there's another category in Dave Hartzell's field notes that's much softer, but arguably just as critical: the silent threat. Hissing and bubbling.
Yeah, hissing and bubbling are fascinating because they don't indicate a mechanical impact or an electrical arc. They signal a chemical escape.
Okay.
Your air conditioning system doesn't actually create cold air, it moves heat. And the vehicle it uses to move that heat is the refrigerant. It's a specialized chemical engineered to absorb massive amounts of heat as it boils from a liquid to a gas, and then release that heat as it condenses back into a liquid.
And this entire phase change magic trick requires the refrigerant to be trapped inside a heavily pressurized continuous loop of copper piping.
Yes, it's a completely sealed thermodynamic loop between the indoor evaporator coil and the outdoor condenser unit. So a soft hissing sound points directly to a breach in that loop. Exactly. Because the refrigerant is under high pressure, when it encounters a microscopic pinhole or a stress crack in the copper, it forces its way out. The hissing is the sound of pressurized gas escaping into the atmosphere.
Which brings up a massive misconception I think we really need to address. So many people treat their air conditioner like their car's windshield washer fluid.
Yeah.
They think the system just naturally uses up its refrigerant over the summer and you just call a guy out to top it off every few years.
It's one of the most pervasive myths in residential HVAC. You have to think of the refrigerant loop much more like the human circulatory system.
Right, like you don't naturally use up your blood. If you're losing blood, you have a physical wound. The
Yeah.
closed system has been compromised.
The exact same logic applies to an HVAC system.
Hmm.
If the refrigerant is low and you're hearing that hissing sound, the system has a wound. There's a physical hole in the copper lines or the aluminum fins of the coil. Sometimes you'll actually hear a bubbling sound instead of a hiss.
What causes the bubbling? Is the refrigerant boiling at the site of the leak?
It's actually the compressor oil.
Oh, really?
Yeah, the refrigerant carries a specific oil through the lines to keep the compressor lubricated. When a leak occurs, that oil often pools around the tiny crack. As the pressurized refrigerant gas forces its way out through that pool of oil, it bubbles.
Makes sense.
Now, if you hear a very loud, aggressive hiss, like a heavy truck tire rapidly deflating, that can indicate an extreme overpressure situation inside the compressor itself, where an internal pressure relief valve has been forced open to prevent the shell from rupturing.
Wow. So the idea of just pumping more fluid into a hissing system is just absurd. You're just pouring refrigerant into a leaky bucket.
Just topping it off without fixing the hole means the new refrigerant will immediately leak right back out. This requires a professional equipped with specialized temperature and pressure gauges.
Right.
They have to measure the exact superheat and subcooling of the chemical to pinpoint how much is lost, locate the microscopic wound, patch it shut, pull a deep vacuum on the system to remove all moisture, and then weigh in the exact factory charge of refrigerant.
So again, the actionable advice. Turn the unit off. Do not sit on a hissing sound for weeks while the system slowly bleeds out its lifeblood, right? Because the compressor overheats from lack of return gas.
Exactly. The compressor relies on that returning cool refrigerant gas to keep its internal motor windings from burning up. If the chemical escapes, the cooling mechanism for the motor escapes with it.
Okay, so we have thoroughly mapped out the haunted house of HVAC sounds. We have the structural rattles, the electrical buzzes of failing capacitors and contactors, the screeching of scorched bearings, the heavy banging of broken compressor springs, and the chemical hiss of a punctured sealed loop.
It's a lot to process.
It really is. So, how do we establish a baseline? What should the listener be listening for on a normal, healthy day?
Establishing a baseline is crucial because we don't want people hyperventilating every time the machine kicks on. A healthy system makes predictable, rhythmic noise. For instance, a solid, distinct click when the system first turns on is perfectly normal. That's the contactor we discussed earlier doing its job correctly, snapping shut cleanly and firmly.
The electromagnet pulling the heavy contacts together without any of that 60 hertz chatter.
Exactly. And once it's running, you should hear a steady, continuous, low-frequency hum from the outdoor unit. That's the sound of the compressor pumping and the fan blades moving massive amounts of air without any internal restriction.
And indoors.
Indoors, it should just be the sound of rushing air and maybe the gentle sound of water dripping.
Which is just the natural condensation draining away. The indoor coil gets cold, it pulls the humidity out of the warm air in your house, and that moisture drips down into a pan and drains outside.
Right. It's just a byproduct of the thermodynamic process. You
Yeah.
get so used to the specific baseline that you just tune it out. It becomes invisible to your ears.
It's kind of like learning the normal settling creaks of your house, right? Once you know your house's normal baseline, you immediately know when a footstep sounds out of place. And that's the superpower here. Because you know the baseline so well, the moment a new frequency is introduced, a slight bearing squeal, a subtle vibration, it instantly stands out. You don't need an engineering degree to know something is out of place. You just need to trust your ears when the pattern breaks.
The ultimate signal is deviation. A new sound that wasn't there yesterday, or a normal hum that suddenly grows dramatically louder over a period of weeks. That deviation is your early warning system.
And this brings us right to the specific advice from our source today. Dave Hartzell has seen every single one of these failures firsthand over 47 years.
He's seen it all.
Oh, for sure. His directive to homeowners is incredibly clear. If your air conditioner is communicating a deviation, if it's buzzing, grinding, screeching, or hissing, do not just turn up the television and hope the machine fixes itself. Listen to what the equipment is telling you. Shut it down if you hear mechanical violence. And if you've ruled out the basic external debris causing a rattle, you need trained eyes and specialized gauges on the equipment.
Understanding the physics of the sound empowers you to act decisively rather than reacting out of panic.
And for anyone dealing with these auditory red flags, Dave explicitly tells listeners, if you need a professional who understands exactly how to diagnose and repair these intricate mechanical and electrical failures, call Hartzell's Heat and Air at 405-375-4822.
Right.
They are located at 602 South Main in Kingfisher, Oklahoma. That's Hartzell's Heat and Air at 405-375-4822. Leaning on 47 years of NATE certified expertise to actually solve the physics behind the noise, not just put a Band-Aid on it.
If we pull back and look at the bigger picture, decoding this specific machinery changes how you interact with your entire environment. It really raises a fascinating concept for you to consider today.
Oh.
Think about the complete acoustic footprint of your home. Now that you understand how to actively listen to the thermodynamics and electromagnetics of your air conditioner, what other hidden machinery is speaking to you?
Oh, wow. That's a great point.
Right. Your refrigerator, your water heater, the pump on your washing machine, they all rely on bearings, relays, and pressurized loops. What kind of hums, clicks, and grinds are radiating through your floorboards right now that you've simply been tuning out, just waiting for the day it's too late?